Hey, welcome back to our notes from Unit 8, Lesson 1. We're looking at example 3 with limits and 3 different types of discontinuity that can be observed algebraically by looking at the limit statements. So if f of x has a removable discontinuity, and remember removable discontinuities from earlier in the year, we learned those are holes in the graph. Okay, that removable discontinuity at x equals a occurs when the limit as x approaches a of f of x is not equal to the function evaluated at a. Okay, if we flip over to the back of the notes booklet here in example 4, okay, there's a place where we can sketch a graph of that situation to use as reference when we're doing problems that involve discontinuity. So if the limit as x approaches a of f of x does not equal the function evaluated f of a, that means that we're going to come from the left and the right and approach the same value of a. So for example, if I had a function that came down to here, right, hit an open circle, and then went off in another direction, right, this circle, open circle, would be at A. Okay, and that would be an example, not the only example, but just an example where the limit as x approaches A of f of x is defined. Okay, it exists. And now we need that not to be equal to f of a. So having the open circle there, f of a would be undefined in that case. If I want f of a to be defined, then I would have a closed circle at some other y value other than my limit here at the open circle. So that would be what a removable discontinuity would look like. Okay, our second definition says that f of x has a finite discontinuity, also called a jump discontinuity at x equals a, when the limit as x approaches a from the left of f of x is not equal to the right-sided limit approaching a. So if I look at the back of the notes again, under non-removable discontinuities, a finite discontinuity or jump discontinuity, my limit from the left cannot be the same value as my limit approaching from the right. So if my function is coming from the left, here I hit that value at a with an open circle, then my limit coming from the right has to end up at a different y value. Now, it says nothing about whether f of a has to be defined or not, right? I just have to have it be a function with limits that don't converge in the same spot. So this would be a perfectly fine example. I could also fill in one of these endpoints. That would be fine. It would still be considered a finite or jump discontinuity. It's non-removable because I can't repair it. Right? If I just have a hole, I can plug that hole in my piecewise function and then it would be continuous. But there's no way for me to plug this hole. If I were to try to make both of these filled in, then it wouldn't be a function anymore. It would fail the vertical line test. So this is non-removable because it can't be fixed. Okay, then in my third definition, f of x has an infinite discontinuity at x equals a when the limit as x approaches a of f of x is equal to infinity. And remember that doesn't exist. It's just telling me that the graph is bending and going up to positive infinity or down to negative infinity as we approach from the left and the right. So looking at that graph in example 4, an infinite discontinuity where this limit statement would be happening would occur whenever you have a vertical asymptote at A. So as my graph comes from the left, right, it can't touch or cross, so it's going to bend and go along the asymptote. And then when my graph comes from the right, same thing, it can't touch or cross at vertical asymptote, and so this would be an infinite discontinuity. There's nothing that says that these have to go in opposite directions, like the parent graph of the rational function. So we could, if we wanted to, have both ends headed up to positive infinity, or we could have both ends headed down to negative infinity. You know, any of those combinations would still be an infinite discontinuity because the vertical asymptote guiding the graph. So now that we know what they look like and how they behave graphically, we can use that to sketch the graph of a function f that satisfies all of these conditions. And then we're gonna, once we have the graph sketched, identify the x value of each discontinuity and classify its type. So statement A says the limit as x approaches 3 of the function f equals 4. So I'm gonna go to where x is 3 on my graph, and then up to where the y is 4, and that's going to be a stopping point whether I'm headed from the left side or from the right side, right? That's what this statement is saying, that left or right side, I'm going to come to this particular point. Okay, then f of 3 has to equal -1. That tells me I can't fill in this circle because the function is equal to -1 when I substitute in a 3 for x. So I have a closed circle on my graph at the point 3, -1, and I have to pass the vertical line test, so I know that A, the statement A, has to be an open circle. Okay, then in C, the limit as x approaches -2 from the right side for the function f equals 1. So at -2, I'm going to have my y value here at 1. And again, I'm going to leave it open unless I see something that tells me it's closed for now. And that is a one-sided limit. So I'm only approaching it from the right side and headed toward 1. Now D says that the function is increasing on the interval -2 to 3 non-inclusive. So these are x values, remember, for intervals of increasing, decreasing, and constant. And since we're increasing on this interval -2 to 3, that means this point is going to connect with this point, right? It's not going to connect with the closed circle at 3, -1, because then I would be decreasing and f has to be increasing on that interval. So it doesn't specify whether it's linear, whether it's quadratic, or maybe it's a radical function, right? But I'm just going to keep it simple and make this linear. So I'm connecting these two open circles to satisfy part D. So I know B is done. I know D is done. I have not yet completed A because I have to extend that off in another direction. C is good enough because I'm approaching from the right, approaching -2 from the right, and it equals 1. So C is good to go. Okay, E says the limit as x approaches -2 from the left has to be greater than the limit approaching -2 from the right. So I have to have some other value that's approaching -2 and it's coming from the left, and it has to have a y value greater than this one, greater than -2. Or sorry, greater than +1. So I'm going to go up to, let's do +3. Sounds good. 3 is greater than 1, so that would work. There's nothing that says that it has to be open or closed, so I chose to make it closed. And there's no more restrictions that tell me whether things have to be increasing or decreasing, so I'm going to go ahead and make this one constant. Right, it's dealer's choice. So this is a constant function along 3, and it terminates with a closed circle at -2 in the x direction. Okay, and my limit on the left-sided interval is greater than my limit coming from the right side. So that one is taken care of. So that only leaves me with finishing up condition A. The limit as x approaches 3 has to equal 4. And we have our closed circle here, but it's a two-sided limit because I need to come at this from the left and the right since there's no plus or minus as a superscript after it. Now it doesn't say after 3 that it continues increasing, so I'm going to change directions and either go constant or start to decrease. So I'm going to decrease, and there's my graph. Okay, now this is not the only solution by far. There are infinitely many ways you could create a piecewise function that would meet these criteria. You just want to make sure first that you met all the criteria that were listed and that your graph, whatever you created, passes the vertical line test because it has to be a function. So now that we have sketched a graph that meets the conditions, next we want to identify the x value of each discontinuity and classify its type. So our first discontinuity we come to is here at x equals -2. And we can see graphically that that's a finite or jump discontinuity. And when we look at the limit statements, we can see that algebraically that the limit approaching from the left is a different value than the limit as we approach from the right. Right? The limit approaching from the left is 3, and the limit approaching from the right is 1. They're not the same. So x equals -2 is a finite discontinuity or jump discontinuity. Okay, then our next point of discontinuity we come to is here at x equals 3. And this time the left-sided limit and the right-sided limit do have the same value of 4. But the function does not evaluate to 4. The function evaluates to -1 at that x value of 3. So x equals 3 is a removable discontinuity. So x equals 3 is removable.